In this video, we're going to go through the exercise of assembling a 4-stage binary counter on a breadboard. And we're going to do this using the diagram we've got here, which cascades 4 D-type flip-flops. And what we're going to do is assemble the circuit and hopefully end up with something like this. If you want to be put off or daunted, it's a bit more complicated than the circuits we've looked at previously. But the idea is that we're going to assemble this together and get something that operates with 4-bit output that counts down actually from 15 down to 0. So before we sort of disassemble this and start from scratch, let's just talk a little bit about some of the theory that's behind this, because what we're doing is we are assembling a circuit in such a manner that it counts up in 4-bit binary aggregates, so 4 LEDs that we saw before, in sequence such that they form 16 possible combinations. And ours is actually going to count down. So rather than from 1 to 16, technically we should be referring to 0 to 15, but there's still 16 combinations there. And ours is going to count down from 15 all the way down to 0. And the way that it's going to do that is because it will exhibit these combinations as it goes down. Now, I've got my example here again. What we can do is hopefully see this in practice, but it's in the reverse orientation actually. The LEDs are backwards compared to the combinations that we have here. So let's have a look. So what we can see hopefully is as these LEDs sort of go through the combinations given, they're going to correspond with the numbers that we get here. Let's just wait till we get a 0 for all of them. All the lights are off, which is here. So now 1, 1, 1, 1. And we can see that we're going through each of the different combinations here. And these correspond with those in the table, all the way down until we get to 0. And that's the idea behind what we're constructing today. So now we're back to the start again. Okay, so we're back. And what I've done is I've taken everything out, but just left the dual inline chips in situ. The 555 timer on the left here, and these 4013s respectively. I've just lifted them out slightly. One thing I will just caution people now, don't make the mistake I made. When you're taking these out, try if you can to sort of leverage them evenly at both sides, rather than sort of lifting out of one side, because what happens is all the legs get bent and it's very difficult to get it back in place again if it's not useless altogether. So I've spent some time sort of straightening these out again because I made that mistake. But basically, we're just going to put these in situ here, either side of that groove that runs down the middle of the breadboard, the purpose of which is for dual inline chips like these, so that the top legs aren't connected to the bottom legs by those vertical conducting rows that don't conduct over that groove, like we talked about in that first introductory breadboard video. And that's for this very purpose, so that we're not short-circuiting all of the pins of our dual inline chips. So I'm just going to put those firmly into place again there. And same with that 555 timer. We have those now in place. What I'm going to do is I'm probably going to start with the 555 timer actually, and just get a nice clock count going. And then we know that that's ready, and we can start worrying about the rest of the circuit here. So to do that, what I've done is I've borrowed a diagram from Wikipedia actually. It's this one here. If you just look up the 555 timer on Wikipedia, you can find the same diagram somewhere on that page. But what we've got here is a diagram of the circuit that we're going to create, but also helpfully, the diagram also has pin numbers on as to which pins correspond on the actual chip itself. So recalling our last video where we made an active filter, the pins are counted from left to right and then from right to left along the top. So we have 1, 2, 3, 4 along the bottom, 5, 6, 7, 8 along the top. That's for an 8-pin chip. Here we have 14-pin chips, 7 and 7, and that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 along the top. And so one thing to bear in mind is to make sure that the chips are oriented correctly in order to make those pin numbers correspond. We're looking for one of two things. We're looking for either, I don't know if you can see that there, a kind of dot which corresponds with pin 1 on the left hand side, so we know that that's in the correct way, or we're looking for a notch which we have on these. If you have a look at the very leftmost end there, we've got this sort of notch cut out which again corresponds with the pin 1 end, and so those are oriented correctly. It's a little bit misleading because these have a dot as well actually on the other end, which is not brilliant design in my opinion, but the notch kind of takes precedent there because that's a bit more obvious. It's not in the video, but it's actually sort of like cut out of the actual shape of the housing there. So we've got all those chips in the right way anyway. So ignoring this side for now, we're just looking at the 555 chip. And also from Wikipedia, it was very useful. It gave some exemplar values for the components that dictate the timing of the count. So this is an astable circuit, and the clue's in the little diagram there. It produces this kind of square wave output. It's on for a while, then it's off for a while, it's on for a while, and then it's off for a while. And the speed at which that takes place is dictated by these passive components that are connected to the 555 timer chip itself. Namely these three here, R1, R2, and this capacitor C. And what I've done is I've picked out some values for that's going to give us roughly a 1 hertz count. So otherwise, in other words, it's counting in seconds, 1 hertz, 1 second. So we're going to get a roughly 1 second count to correspond with the output here to feed our counter. And to do that, the values that we're going to use are 8.2K or 8K2, 8,200 ohms for R1, 68K, 68,000 ohms for R2, and 10 microfarads for the capacitor. So let's go ahead and try and assemble that. Another small amendment we'll make here, just for the purposes of what we're doing today, just to visualize it, is this output here is obviously going to connect to the counter circuit further on down the line, but we're going to add in just a resistor and an LED here, just to visualize that counter is definitely working at the sort of right speed that we expect. So let's go ahead and put that together. Again, it's best to put that 555 chip in first, because it's kind of the core of the circuit, and place everything in situ with respect to that chip. So first of all, I notice here that pins 4 and 8 connect to the positive power supply. Again, like in previous, what we're going to do is we're going to just use the top rail here as our positive connection, and the bottom rail as the negative connection, like so. And all I'm doing is just using a PP3 battery snap. I'm going to take that off for now, but that's where that would be in place. And what we're going to do is we're going to use just some wire links here to connect pins 4 and pin 8 to the top rail of the power supply where the positive would be. So again, just counting in the same manner as previously, we're counting 1, 2, 3, 4, 5, 6, 7, 8. So pin 8 is this last one on the top row there, and that's going to connect to our top rail of our power supply, like so. What we can do is the same for pin 4. We can take pin 4 and connect it to the top rail like so. Or we could take pin 4 and connect it to pin 8, knowing that pin 8 is then itself connected to the top rail. Either way works. Similarly, pin 1 connects to ground. I'll use a blue. So pin 1 connects to our ground, or a 0 volt connection there at the bottom. So pin 1 going to the bottom there. You'll notice here we've got this capacitor that also goes to ground. I'm going to try and get away with not using that actually. I don't think it'll make any difference to the purposes of what we're doing. So we can ignore pin 5. All that remains then is these 3 components here. And what we're going to do is just do those one at a time. We said that R1 is 8.2K. So I have here's our 8.2K, grey, red, red on the resistor color code. And that's going from the top rail to pin 7. So nice and easy, hopefully, we can take that 8K2 from the top rail to pin 7, and it'll look something like that. And from pin 7 we go through R2, and that connects to pin 6 and pin 2. Let's ignore pin 6 for now. Let's just suppose that we go from pin 7 to pin 2 through R2 there. And R2 we said was 68K. So here we have our 68K resistor, which is blue, grey, orange. And we said he's going from 7 to 2. So from 7, which is the same as that previous resistor R1, the same row, to pin 2, which is sort of directly opposite it. So we have something like that sort of leapfrogs over the chip from pin 7 on the top to pin 2 on the bottom there. Now we neglected this pin 6 here, and the reason for that is we can just solve that with a wire link simply enough. So that's going to take us from 2 to 6, this extra little connection. So from pin 2, which is the same row that resistor ended up in, so pin 2 going to pin 6, if I can get it in, there we go. We end up with something like that. So from, I'll move that one out of the way and that one out of the way. So from pin 2 to pin 6. So what remains then is just to, oh, I forget the capacitor, sorry. We've got this capacitor here, 10 microfarads. He's going to go from either pin 6 or pin 2, it doesn't really matter, but pin 2 is more convenient because it's going to ground, and pin 2 is already quite proximal. And so we want that capacitor going from pin 2, if you can see there, from pin 2 to ground. All that's left then is just to add this little extra bit on that we've proposed, this little LED, just to visualize that count. And that comes from our output. Output's pin 3. So again, going along the bottom, 1, 2, 3 takes us to this row we've not used yet. Pin 3 there. And I'm just going to take this this resistor out to a row off to the side here that's not being used. It doesn't matter which one. But from that same row, we want to connect our LED. Remember, LED being a diode is a semiconductor, and we want to look for that flat edge which signals the negative side, or you can look for the leg that's slightly shorter. I've bent these two legs a little bit so it's not as obvious, but one leg is slightly longer than the other, if you can see that. So we want that shorter leg, or we look for the flattened side to the fascia there. Anyway, that shorter or flattened side is the negative, and that negative is going to go to our little ground rail along the bottom. So I've taken that LED from the same row that resistor ended up, that same row through the LED to ground. Okay, so when we now connect up our battery snap again to the positive, straighten that out a little bit, to the positive and negative rails respectively, what we're hopefully going to see is basically a flashing light. It's going to be our 1 Hertz count, which is all we're hoping for now. And there we go. So we've got our 1 Hertz clock pulse. Okay then, so with that being done, let's remove that battery snap. Actually, before I do that, one thing I'll mention is, again, just like in some of our previous videos, to remember that this particular breadboard, the rails don't extend the whole length of the breadboard. So you can see there's a gap top and bottom, and that rail is separate to that rail, and likewise that rail is separate to that rail. Now I want this battery to sort of supply the whole rail, because we're going to be using it for this side of the circuit as well. So one of the very first things that I'll do is I'm just going to join the top and the bottom rails respectively, like that, with these sort of like little jumper leads that sort of leap the gap. And that just means that we've now got one continuous rail that runs along for the very top and very bottom rows. Anyway, I'm going to lose this power supply for now. One other thing as well, just while I'm on the topic of these battery snaps, it's a good idea not to do what I've just done and just pull the wires out and leave the battery connected, because these two wires can often sort of drift quite close, and what you don't want is for these to touch and to get a short circuit or anything like that. So it's a good idea to disconnect the battery altogether. If the battery comes with a little cap, little rubber cap to stop any short circuits as well, because what you don't want is the battery sort of, the terminals touching something that's going to short circuit the battery, because then problems occur. And so it's a good idea just to disconnect that altogether when you're not using it. Anyway, so what we've got now is the left-hand side of the circuit sorted. We're now going to look at the right-hand side, which is actually sort of our main circuit, this counter. And we had this diagram to go off for that purpose. So we're going to start off, it looks very simple here. And it is very simple, actually. Once we kind of get into the swing of it, there's not that many connections to make. But when you saw the circuit at the start, there was lots and lots and lots of wires and jumpers and leads and connections. Most of them were just tying unused pins to ground. And the reason for that is because these chips are very sensitive, and whilst we're setting this 1 Hertz clock input, any sort of like little noise or signals or movement or anything like that, it interprets it accidentally as a count, and so it starts counting very quickly and out of sync and all that kind of thing. So that's because we need to have all of the pins that we're not using tied to ground, connected to ground, so that signals aren't misinterpreted so easily. So for the purposes of what we were just talking about, I want to just expand a little bit on this diagram. And what I've done, just to make it a bit clearer, because it's a bit small, I've marked on the sort of the 4 sort of important connections involved in each stage. And they are D for data, C for clock, Q is our output, and not Q is basically the opposite of whatever the output is. And the behavior of a D-type flip-flop can kind of be summarized in one little phrase, and it's Q follows D after the next clock pulse. So what I mean by that is, whatever D is, Q is going to copy it, but it'll only copy it after the next clock pulse. Now, our clock pulse is happening every second, which is reasonably regular, but it means that if D's 1, then Q will also become 1, but it'll also only change after the next clock pulse. And likewise, if D is 0, Q is also going to become 0, but only after that next clock pulse happens. Not Q, we said, is just the opposite of Q. So whatever Q is at any point, not Q will be the opposite. So if Q's 1 or high, not Q will be 0, and vice versa. If Q's 0, not Q will be 1 or high. So that's the basic summary of the D-type flip-flop and how it works. But we're going to sort of cascade 4 of them together in this manner. And the way we're going to do that is by referring back to this pin-out connection for the 4013. Now, we mentioned before that the 4013 chip that we're using is a dual package in that it has 2 flip-flops in one package. So we have a chip for these 2, and we have another chip for these 2. And what you'll notice if we look at this pin-out connection is that we have things like Q1, not Q1, clock 1, D1, and likewise we have Q2, not Q2, clock 2, D2. So we have 2 sets of everything for this purpose. So when we come to assemble this circuit here, we're going to first of all take the output of our clock that we made. This was our Astable circuit, and you'll see that that connects to the clock input C of our first chip here. And so what we can do is very simply, just by using a wire link, what I'm going to do is I'm going to use green. I'll try and give it a bit of a color code. I'm going to use green for outputs and inputs and things like that. So from the clock Astable circuit that we made, and if you remember, the output pin was pin 3 on the Astable. We connected an LED, the resistor and the LED to it, but pin 3 was our output, and I'm going to take pin 3 and I'm going to connect it to the clock input, or clock 1, from our first chip here. And so again, back to this diagram here, clock 1 was pin 3 again, actually. So clock 1, pin 3. And so all I'm going to do is I'm going to take that connection to pin 3 of the clock on our first circuit there. So there it is, if that's any better to see there. So we're going from pin 3 to pin 3. Okay, so next, the only other thing for this stage really is this little loop that comes round from not Q round to D. And again, it's still the first stage of the first chip, so it's not Q1 connecting to D1. And so again, referring back to, I'll try and put these side by side actually. We're going from not Q1, which is pin 2, to D1, which is pin 5. So for these little loops, we'll use, what will we use? We'll use orange for these. So from not Q1, which we said was pin 2, to pin 5 for D1. 1, 2, 3, 4, 5. So we have just a little loop like that from pin 2 to pin 5, like so. And the idea behind that is we've got this little loop here that feeds the data. D is fed from the inverted or the not Q output at each stage. You'll notice that each stage is identical. So that's the first stage complete, really. We're going to do the same thing. You can kind of get the sense from the diagram here. We're going to do the same thing 4 times pretty much. And so rather than the clock Astable feeding the clock input for the next stage, the next stage, its clock input, actually comes from Q of the preceding input. So Q1 is going to feed clock 2. So again, let's refer to our diagram here. Q1 is going to feed clock 2, so 1 to 11. And that's one of our sort of inputs, our clock inputs. I was using green, I think, for that, yeah. So Q1, pin 1, is going to connect to pin 11. And so we end up with something that just sort of leapfrogs over the chip like that, from pin 1, bottom left, to pin 11, which is the middle on the top there. And we need that loop for the second stage, not Q2, we're on chip 2 now, not Q2 is feeding D2. And so again, it was orange, I think, for these little loops. Not Q2, pin 12, feeds D2, pin 9. So we have pin 12 to pin 9. We have something like that orange one there. Second stage done. The Q output from that stage is going into the clock input of our third stage. Now our third stage, we're now over onto the second chip. Remember that the first chip was for stages 1 and 2. 3 and 4 are going to be what we're calling 1 and 2 again for the second sort of half of the circuit. So what we have here is the Q output Q2 from the first chip is going to be feeding clock 1 of the next chip. So again, I'm using green. I'm running out of greens here. Here's another green one. Q2, which is pin 13, is going to be feeding clock 1 of the second chip. So Q2 from the first chip, pin 3 from the first chip, feeding, pin 13 from the first chip to pin 3 of the second chip. So we have something that looks like this. We've got pin 13 of the first chip, Q2, leading to the clock input pin 3 of the second chip. We have something like that. And then this loop here, not Q to D. Well, we're back to 1 again. It was 1, 2, 1, 2, going by this numbering system. So not Q of 1 is going to D1. So again, not Q of 1 is 2, D1 is 5. So 2 to 5 in orange, 2 to 5. We have something like that. And again, you'll notice it's starting to look like the mirror image or the repetition of the first chip here. We're repeating ourselves again. So there's our loop there for the third stage, which is now complete. Last stage, we're going from Q1 to clock 2. And again, Q1 is pin 1, clock 2 is 11, and that was a green connection. So we're going from Q1, which was pin 1, to clock 2, which was 11. And then the last connection to make, not Q of stage 4, is going to D of stage 4. So not Q2 to D2 on the second chip. So not Q2 pin 12 to D2, which is 9. And we had orange leads for those. So we're going from not Q2, which is 12, which is there, to D2, which is 9, which is there. Okay, so we finished the connections that were in the schematic here, and it doesn't look anywhere near as complicated as what we saw at the start of the video, but unfortunately there's a couple of extra things to do. First of all, we need a power supply to each of these chips, and so what we have here, if you notice, are these VDD and VSS connections. In other words, positive and negative. And we have that twice, obviously, because we've got 2 chips. And so what we're going to do is we're going to connect VDD, which is pin 14. That's our very leftmost on the top row. He's going to go to positive. And then pin 7, which is, if we're looking in that orientation, bottom right, pin 7 is going to go to negative. So we have pin 7 down to that bottom rail there. And likewise, exactly the same for the second chip. We've got pin 14 going from there to the top rail. And we have, let's find a wire, pin 7 going from bottom right to the bottom rail. So we end up with something like that, negative, positive. The last thing, unfortunately, is a little bit of an awkward one. Because of the sensitivity of these flip-flops, they often sort of misfire or misread and miscount unless we tie some of the unused pins down to 0. And so what I mean by that is there's a few pins that we've not discussed yet, like set, reset, that kind of thing. And what I'm going to do is I'm going to basically, all of the pins, just scanning along, any rows or pins that we've not used, I'm going to connect them all to the negative rail. And so we have reset 2 and set 2, which are pins 8 and 10 respectively. So I'm just going to use yellow wires for this, just to give it a little bit of a color code. So it's these 2 here on the diagrams, reset 2 and set 2. I've not used these. We don't need to use these. I've taken both of those and I'm connecting them down to that negative rail. So they're going to go in like so, just these yellow connections here. Likewise, set and reset 1, 4 and 6 respectively. Again, I'm just going to take 2 more yellow wires here. I'm going to take both of these 4 down to 0 and 6, if I can squeeze it in there, 6 down to 0. And we're going to do exactly the same on the other chip here. Okay, so now we've got all of those in place. There's no sort of rhyme or reason. I've just sort of found spaces along the bottom here for them to be tied down to 0. Any of those pins that weren't being used, basically. That's our circuit complete. Now, as it stands, this could be happily counting away, and we don't really know or can't really tell what's going on. And so the last thing that I want to do, which isn't on the schematic, is just to connect some outputs in the forms of LEDs so we can actually see the count taking place. And so to do that, what I'm going to do is I'm going to take 4 LEDs and just making sure that they're all in the right way that we mentioned before. I'm going to put them quite close together. We'll just have to make sure that they don't touch one another, but they're going to go in here. 1, 2, he says 3, and 4. They are crammed together, so just bear in mind to make sure that the legs aren't accidentally touching one another. But there they are, 1, 2, 3 and 4. And if you haven't left enough room on this side, you could do them over here. It doesn't really matter. There could be anywhere, wherever there's a gap. I've got 4 LEDs there. As it stands, the voltage might be a bit too high, as it's sort of like output from the flip-flops there. So what I want to do, I've got 4 330 ohm LEDs, and I'm just going to sort of use those for protection a little bit, by connecting those in series with each of those. So from the same row as each LED, I'm connecting a resistor that's going to go above the break or above the groove in the breadboard. So I've got that resistor going directly up like that. If it was on the same side of that groove, there'd be a short circuit because it would be directly connected. But because it's that groove, I can be in the same row. I've got 1. I'm going to do the same thing again. So they're in place, but there's a lot of sort of bare legs. This is a bit bad practice. You're supposed to sort of trim these components down, but as long as we make sure that those legs aren't touching one another, that's getting a bit precarious there. But we'll be all right, I think, for the sake of this. If you want to be a bit neater, you can trim the legs down so that they're only as long as they need to be, kind of thing. But we'll be all right. So there's our 4 LEDs, 4 resistors. Each of those is 330 ohms, orange, brown, going that way, orange, brown, gold. 330 ohms, which is enough to just protect these resistors, these LEDs, for the purpose of what we're doing. The last thing is simply just to connect each of these 4 LEDs to the 4Q outputs. Now, remember at the start, I sort of turned mine upside down because it was counting backwards. I'm going to do a bit of a better job this time, and I'm going to connect them in the reverse order, or the correct order. And so the first Q is going to correspond with the last LED. I'm going to do them in reverse order. So as we go from each Q, these are our outputs. They're going to connect the LEDs, but I'm going to connect them in reverse order. So that'll be our first Q, second, third, and fourth. So nice and easy, hopefully, because we know where the Qs are. They're pin 1 and pin 13, respectively, in each stage. I'm running out of colours here, so I'm going to use, we'll see if we can get away with white. So we have Q1. Let's see if this will stretch. So Q1 from the first chip is pin 1. So let's see if he'll go in there. So right in the first pin 1 of that first chip there. He's going to feed the rightmost LED. So I want it in the same row as the last LED, as it were. Likewise, Q2, which is pin 13, is going to feed the next most rightmost LED. So we've got pin 13 on that first chip. This is starting to get a bit of a mess now. Pin 13 there. So second from the left on the top row, pin 13 is going to the second rightmost LED. So in it goes there. And then the next Q is coming from the next chip. Now we're on to Q1 of the second chip. So pin 1 of the second chip. This is going to become a bit of a jungle, but pin 1 of the second chip. Let's see if we can just snake this through here. And that's going to be on next LED. And then finally, Q2 of the second chip, so pin 13. A little bit easier, this one. Pin 13, second leftmost pin on the top row. Pin 13 is going to be our last LED output. Okay, so now we're all done, hopefully. Let's connect this up and see if it works as expected. So we've got our battery snapback for this purpose, and because we tied the sort of left half of the rail to the right half of the rail, top and bottom, it doesn't matter whether we have our battery snap on the left or on the right, it's going to work out the same either way. I'm just going to use the left because we've got a bit more room on this side. And then we just need to connect to, I'm just using a normal 9-volt battery. We now have our counter circuit. And it should, hopefully, if I can find the diagram table from earlier, we now don't need to flip this circuit upside down like we did at the start. We've got, we're counting down sequentially with these in the right order now. So I hope you found this video useful, even though it was long and quite a little bit awkward at some points. I hope you can make out the build as it progressed there, and that it's been useful if you're following along as well. But there's our 4-bit binary counter just using D-type flip-flops.